Okay, this presentation is going to be about an introduction into what's called the pgcrypto contribution module. And it's a very basic introduction, what I want to do. And I like doing these kinds of talks because it helps sharpen me about the basics. There are concepts to learn. The concepts, when it comes to encryption, is actually quite sophisticated, but its implementation in Postgres is quite simple. The pgcrypto module has actually been around since almost as long as Postgres has been around, when it first was open sourced in the 90s. What it is a suite of function calls, procedures that allow a various functionality using under the large umbrella of encryption. And what we're going to do is basically go through a very basic, how to install it, recognize what certain features are. Basically, this is about concepts. The concepts are the harder things to wrap around. So again, reiterating, it's a collection of functions. It permits you to create and administrate a database system capable of handling encrypted data. So we're beginning here. As usual, I use my preferred distribution is Ubuntu because of the libraries, the versatility available in the environment. And I'm using the most recent version, which is Bionic. Installing everything as per the download process. And in this particular case, what you'll notice is we're, in addition to installing the standard libraries of Postgres, we're installing the GNU PG2, NetTools, and Systat. NetTools and Systat are for my own edification. They contain utilities that help me monitor the system as it's under load, as it's being used. The GNU PG2 is actually the encryption libraries that allows you to use some of the features that pgcrypto uses. It assumes that you're going to have pgcrypto on your server, and it enables certain particular concepts like public key encryption. So we check our server, it's active, and we log in. We're going to create a little database called demo. And when we're in demo, we're going to create an extension called pgcrypto. This is the list, the most recent, of the implementation of all the function calls used in the pgcrypto. Now, the thing you need to understand is what we've got are a collection of functions of concepts that were developed over the years. What Postgres did was it basically pulled in all the concepts at the same time. Some of these concepts, some of these ideas are behind the scenes. Some of them are, these function calls aren't really used as often because they've been superseded by what are now considered better industry practices. What you're going to see is an overview of all of them. It's very helpful to know them because of the ideas behind them. So we've got armor, crypt, de-armor. Like for people coming up to pgcrypto, these are words that absolutely mean no sense. They encrypt, you can figure out. HMAC, HMAC, generate salt. The decrypt, publication, encrypt, publication, public. They're there. So let's go through them. The classifications are as follows: general hashing, passwords, random data functions, raw encryption, and PGP encryption functions. General hashing functions are actually used all the time under the scene. Its most primitive are CRC checksums. The internet protocol, for example. When we have packets sent back and forth on the internet, not only is the information, the data sent, but there's a checksum of that data, a representation of the data that is sent with it too. That's why you have slow bandwidth sometimes, because it's your application is going to get these packets. They're going to say, hey, this doesn't make sense. My checksum doesn't equal the data. That means there's corruption, and it'll reload, it'll re-ask for the packet, and you wait until it comes back in. On a more complex, bigger level, if you go to the Postgres site, if you go to our sites, the Percona, you find that when we have downloads, we also include the hash. A hash is a unique fingerprint. It's an algorithm that goes in and it looks at whatever the content is, and it generates an alphanumeric series of numbers that is unique. Now, over the years, we've had different protocols. The most common one everybody knows is MD5, but before that, we had MD2, MD4. Now, MD1 and MD3, they were sort of like, they went up and then they went down. Nobody really knows where they are these days. MD4 was actually a very popular, very fast algorithm generating a hash. It was deprecated in favor of MD5 because of the statistical probability of what are called collisions. That statistically, it was possible that you would have a combination of bits and bytes that would come up with the same checksum that would match something entirely different. And this is one of the issues about when you're doing encryption. You're concerned about people corrupting, changing something. The checksum guarantees it. The MD5 a few years ago was identified as you could generate collisions. Is it practical to do a collision? It depends on the use case. You're talking about people that are very advanced when they're trying to do that kind of a thing. Password hashing functions builds on top of the general hashing. You generate a unique fingerprint, say of a password, but in certain cases, you don't want that password to be the same. Like if you have the same password and you generate a hash, when you do an MD5 checksum, that hash will always be the same. And in Postgres, that's exactly how we hash our passwords. It's a username password combination. The hash is not exposed unless you are the super user and can see it. But you can tell that whenever you have the same username and the same password, the hash will always be the same. But when you do a password hashing, that one's different. It uses what's called a salt. And the salt actually mixes things up so that the encrypted form of the password is always different. Random data functions, these are convenience functions. Linux has an implementation. It's the random, I think it's called the random pool. And OpenSSL has a quite extensive library to create random characters. Raw encryption, that's your old-fashioned symmetric encryption. This is where you have a password. The same password that encrypts something is the same password that's used to decrypt. And of course, then you have PGP encryption functions, or GPG, which is kind of confusing because it's either one or the other, and they actually do mean different things. What's important about PGP is it uses checksums, it validates, it puts lifespans on encryption keys, and it uses public-private key encryption, which we'll cover in a few minutes. So when you look at this table here, we see these are all the capabilities of generating hashes. Now, a long time ago, that left column that says built-in, most of that was no. Most of what you wanted to get that functionality was accessing OpenSSL, which pgcrypto actually has a wrapper allowing you to get to the OpenSSL libraries. OpenSSL is the industry standard. Over years, pgcrypto enhanced, built up all those library capabilities to match it. So except for that little sections that says other digest algorithms, virtually everything these days is now incorporated into pgcrypto that OpenSSL does. When it comes to concepts, especially when you start learning about using the crypto module, you'll find that the OpenSSL project, when you go online, is extremely detailed when it comes to encryption. It talks about the concepts. I would suggest that you start there. It's a very deep subject. It's something that a person could actually specialize as a profession. So here's our simple examples. I didn't put out the hashes. I just left an example. The function called digest will generate these hashes. Hello world MD5 is a certain character length and complexity, SHA-256. The RMD160 is actually one of the older the older hashes. And again, this is available also through the OpenSSL. These come under the category of other algorithms supported through the OpenSSL libraries. They're very interesting. These hashes, remember, whatever you put in for the string, when the hash is generated, will always be the same, no matter what. It's just different complexities, different lengths. These days, with what we're hearing in the industry, reports about hacks and penetrations, we are encouraged to use SHA-256 as much as possible, something that's much longer and greater than MD5. It's for that reason why, as you heard earlier in our talks, Scram has been adopted in Postgres. The challenge there is some of the client applications, the frameworks, haven't incorporated the capability of Scram yet, and also some people, they still have to learn the concept. They haven't gotten their head around the difference between MD5 and Scram. HMAC, Hash Message Authentication Code. This is old school. It's still relevant. The PGP libraries do take care of this, but this is really, really interesting. You send a message. You can see the first line, my message, hello world. And then you also include a key. You're sending a message in the clear. You're not encrypting it. What you're doing, though, is you're getting a hash of that string, and you're adding a text called my secret key. Now, that could be any string. The thing is this, the sender and the receiver both have this secret key, this pass. When you send a message and you use something like HMAC, you generate a hash, you send the hash with the message, the person receives the hash and the message. And to verify, to validate whether or not that message actually came from you or came from that other person, you generate a new hash using that secret password. The hashes match, you know the message came from them. Now, obviously, of course, this has been deprecated in favor of signing. When you sign the message, the signature is going to be part of it. This is of a simpler time, a simpler feature. And the nice thing about something that's simpler isn't just about understanding. Common sense, it's actually quicker too. It generates much faster. So you have an opportunity if performance comes as an issue. And when it comes to encryption, performance is always an issue. Below you see encoding. We took the first query, and what we've done is we translated it into a format that could be stored as a byte A in Postgres, or if we had to, as a data type text. Encode and decodes are actually the basis of how emails used to be sent, how it converted binary information into readable format. A long time ago, email could only do 7-bit, which meant alphanumeric, and that was it. Armor, you might recognize this. When you generate a public key, when you have a private key, when you generate messages, if you've ever looked at them, you're going to see it's going to say begin PGP message and PGP message, and then you're going to have your combination of alphanumeric. This formats it. It makes it storable, and it makes it possible to send it through different mediums. Again, the old email standard was 7 bits. Other password hashing. As I said before, you want a password. You want to be able to generate it. It's very useful if you have an application process. Because of the protocols, even though this is a Postgres-specific functions, you should be able to find the same corollary in Python, in Ruby. The libraries are comprehensive enough that when you generate your password, and you can find out what the password is, you can validate it on the other end because the libraries will be there. Now, in this particular case, imagine you have a credit card. Well, we have a concept called translucent data. Never store credit card numbers, never store social security numbers, for example, in a database. Instead, store their hash. If you can, do not store them as standard hashes because they'll never change and it's possible to do brute force. Instead, use a password hash, which will generate a unique hash of the password every time you strike it. In this particular case, as you can see on the slide, we ran these two sets of queries twice. We use the same password, we use the same message, and the hash password actually came out different. And you can see in both times that when you use it, you can validate it. So if somebody sends, say, a credit card information online, it's going to be hashed on his end. It gets sent. If that hash is then validated by comparing the hash there. And those two hashes, even though they're different by the algorithm, they can be compared, they can be matched. Random data functions, encode, decode. You notice the function, generate random bytes. OpenSSL has always had this ability. And if you know a little bit of Linux wizardry, you can do the same thing. You can create random combinations of characters. Again, very useful when you are involved in the whole idea of creating encryption, or in our case, in databases at Percona, sometimes we do benchmarking. And when we benchmark using data, strings, this is the easiest way to generate random data. It forces us to use unique data information to check out the performance of loading and unloading instead of letting the system trying to find matches and making it simpler. UUIDs, they used to be rare birds. Now they're pretty common. Universal, unique universal ID identification. Postgres, for the longest time, you would use a type serial, an incremented number. However, when you start having sensitive data, one of the rules about encrypted data, for example, is you refer to identification numbers, the IDs, which are going to be classified as primary keys. However, you don't want sequential. Sequential is a pattern. Patterns are a weakness when people are trying to hack or understand your system. So you use universally unique identification. If you notice, there are actually 5 versions. There are actually different standards of generating UUIDs based on what your needs are, based on performance, based on bandwidth. Some of them are completely random. Some of them, they pick information like date stamps. Some of them use the MAC address. The interesting thing about a MAC address is that when you do that, you could come up with some interesting hash tables when you partition tables. As you can see here, we're using an example of version 4. pgcrypto has been here for years. You've been always generate UUIDs, and the older implementations of application servers and Postgres use this functionality. However, these days you can also generate UUIDs because now they've been imported as general functions in the most recent versions of Postgres. So you can see here that every time you run the random UUID, you get something new. Raw encryption. Please pay attention look at the bottom there where it says attention. Again, pgcrypto module doesn't incorporate just cutting edge. It incorporates all the major concepts that have been developed over the years. This form, encrypt, decrypt, is what's called symmetric encryption. And on our level, we try to discourage it because the password that you use to encrypt is also the same password that you use to decrypt. Also, you'll notice that you can't do integrity checking. You can't prove that it has been changed or hasn't been changed. You can't sign it. And of course, that little last point there, not handling text. If you look closely at the query example, it was created in the table, populated the table, and we pulled it out, and we had to use an encode and decode, and we had to coerce it between byte A and text. The PGP encryption functions actually handle this. You don't have to do this fancy casting. So let's talk about GPG. You're going to have to install and generate public-private keys. We're assuming that you're on a Linux machine. You could do this on Windows, but it's easier just to demonstrate on Linux. You are going to install it. You are going to generate keys. Then there's going to be a little interaction. You're going to say, okay, who are you? What's your email address? What's the ID? And then it's going to create your full key. You can review it by using the list key. Now, in this particular case, let's look at an encryption. This is, again, simple, symmetrical. Password to encrypt, the same password to decrypt. You can see here, we have a secret message, we have the password, and we take it out, and it comes out again. Again, this is the favored method. It is the most modern method. It is the recommended method. And all these libraries are supported in all versions of Linux. Here's a little interesting example using asymmetrical public key encryption. Remember, we generated our public-private keys. Well, we need to use those public-private keys. The public key is one way. You use the key to encrypt the message. The sender no longer has the ability to decrypt that message. The only person that can do it is the one who generated those keys. The person who reads it, best case, is that when you read data that's been encrypted, you never have the private key on the system. Instead, you read it into your application process. The application process then decrypts it in real time. Then from here, you can see, in this case, we're using PSQL. Let me show you right here. So here's a command, GPG list secret keys. This is the public-private key that we created. User1 at myemail.com. And you see this long alphanumeric combination string? That's how we're going to export our keys. Look down here, GPG2 in ASCII format, you're going to export it. And this is the fingerprint. This is what we're going to use to pull it out. You can have an entire collection of public-private keys in GPG, and it'll just pick out that one, and we're going to pipe it into a text file. Same thing for the private key. We do this so we can do our little demonstration. We're in a PSQL session. Set public key. Now we're going to assign a variable. If you remember your PSQL, the meta command is we're going to create a variable called public key. We're going to create a variable called private key. I'm separating this out for the purposes of clarity. 4 single quotes on the left side, 4 single quotes on the right side, and in here is a backtick. This is bash. So I'm going to cat robber.ask.text, and that's going to go into public key. Private key, we're going to do the same thing, 4 single quotes, backtick, cat robber.secret.ask.text, and that's going to be put into the private key. We verify by just doing a selects, and you notice the colon. Again, this is all Postgres stuff. It's all standard PSQL. Now we encrypt. We're going to do PGP public encrypt. We're going to use the public key. Notice the function call, dearmor. So there's our message. We use our key, dearmor, and we're going to put it into a table. We're going to call the table encrypted message. Now we decrypt. We use the PGP pub decrypt. Notice that we're querying the table. Select message from encrypted message, and we're using dearmor. Notice this time, private key. We use the password because when we created the key, we had a password to keep it. Good practice, don't lose the password. Don't sign keys without passwords. And you can see here, it outputs my secret message. Nice and easy. Performance issues. A long time ago, I was at a talk with Rasmus, the creator of PHP. He was working for Yahoo at the time, and they ran into performance issues when they had Postgres as a back end. It turned out that they had SSL enabled by default, and they didn't realize it. Encryption hits CPU. Always remember that. When you use it, you must take it into consideration. In these days, it's a necessary evil, but there may be use cases where you can decide where you can choose not to use encryption. The rule of thumb is general data. If you want to decrypt, that's a judgment call. Administrative tasks, when you're logging in as a super user, when you're doing replication between master and slave, or these days, primary and standbys, replicas, that's always encrypted. Always beware of the costs. When you do individual pieces of information, again, the concept translucent data. If you can, never, never save the actual information. Save a hash of that information that's sensitive. Public key encryption, policies, common sense. One of the things that is not done is putting lifespans on keys. Always put a lifespan. But keep in mind, if you put a lifespan on data and you exceed that lifespan, you're not going to be able to access that data because your key will no longer be valid. You'll have to do some crazy tricks. So a good practice is to have multiple keys assigned onto your sensitive data, allowing more than one private key access to the data. Symmetric key encryption issues. This is the secret password, where you have the same password encrypting and decrypting. So always watch what you're doing. It's all common sense stuff. Again, what I like about going through these presentations and these talks is it helps me remind myself of the basics. Never forget the basics. And that's it. Thank you very much for your time.